The research paper presents a formal framework for reasoning about translational separation logic verifiers. It focuses on the challenges of defining the semantics of intermediate verification languages, IVLs, that support separation logic and connecting these IVLs to both front-end and back-end verification tools. The authors introduce a generic core IVL that captures the essence of different separation logics and define its operational semantics. They also formally connect this core IVL to two back-end verifiers, which use symbolic execution and verification condition generation, respectively. The framework's usefulness is illustrated by instantiating the core IVL with elements of Viper and connecting it to two Viper backends as well as a front-end for concurrent separation logic. All technical results have been formalized in Isabelle, whole, including the core IVL and its semantics, the semantics of two backends for a subset of Viper, and all proofs. The paper highlights the challenges of defining IVL semantics that capture the generality needed for encoding diverse verification problems and strategies, and connecting these IVLs to backends and frontends while ensuring soundness. This research paper presents a formal framework for translational separation logic verifiers, addressing the challenges of bridging the gap between high-level program proofs using custom verification logics at the front-end level and verification algorithms for separation logic-based intermediate verification languages, IVLs, at the back-end level. The authors introduce a generic IVL, called Core IVL, which captures the essence of different IVLs based on separation logics. Core IVL can be instantiated with different statements, assertion languages, and separation algebras, including implicit dynamic frames used in Viper. The authors define the semantics of Core IVL using dual nondeterminism, combining demonic nondeterminism to verify properties for all inputs and angelic nondeterminism to abstract over different proof search strategies employed by backends. An operational semantics for Core IVL is defined, incorporating dual nondeterminism and parametric in the separation algebra to support both separation logic and implicit dynamic frames. This facilitates proving a formal connection to concrete verification algorithms used in backends, such as symbolic execution and verification condition generation. To address the challenge of connecting the front-end and back-end levels, the authors define an axiomatic semantics for Core IVL and prove its equivalence with the operational semantics. This enables formal reasoning about the entire chain from front-end to back-end. The authors illustrate the practical applicability of their formal framework by instantiating Core IVL with elements of Viper and proving the soundness of two verification backends. A formalization of Viper's symbolic execution backend and a pre-existing formalization of Viper's verification condition generator. They also prove the soundness of a front-end based on concurrent separation logic using their axiomatic semantics. The contributions of this work include a formal framework for reasoning about translational separation logic verifiers, a parametric language core IVL with novel operational and axiomatic semantics, and soundness proofs for Viper's backends and a front-end based on concurrent separation logic. Here is a combined summary of pages 5 and 6 of the research paper. The authors introduce a core language for separation logic, SL-based intermediate verification languages, IVLs, called Core IVL, which captures central aspects of SL-BASED verifiers such as Viper, Jillian, and Very Fast. Core IVL is designed to manipulate SL states via inhale and exhale primitives, which assume and assert logical constraints and transfer resources. The language supports diverse logics and semantics, including separation logics, implicit dynamic frames, IDF, and fractional recursively defined predicates. The syntax of Core IVL is shown in Figure 1, where assertions are semantically represented as sets of states, and expressions are partial functions from states to values. The language includes key verification primitives such as inhale, exhale, and havoc, which allow encoding various statements, including while loops, procedure calls, and proof rules for parallel programs. The authors illustrate the use of Core IVL by encoding a simple parallel program into Core IVL, as shown in Figure 2. The program takes a cell object as input, allocates a new cell, assigns values in parallel, and finally asserts that the result is equal to the input value plus itself. The authors demonstrate how to translate this program into core IVL, using IDF syntax to annotate the example. The syntax ACC, E, V, F, denotes fractional permission, and ACC, page V, underscore, denotes a wildcard permission, which guarantees read access while abstracting the precise fraction. The author's goal is to verify this program in concurrent separation logic, CSL, by encoding the program and the proof rules of CSL into core IVL. They aim to prove that the assertion on the last line of the program holds, using the core IVL language to reason about the program's behavior. The research paper discusses the formal foundations for translational separation logic verifiers. It presents a novel approach to encoding source-level parallel compositions into core IVL programs. The authors demonstrate how their encoding model treats each proof task of the CSL verification problem as a separate IVL method, reflecting individual proof steps. They also explain the operational semantics and backend verifiers, emphasizing the need for a formal connection to various backend algorithms. The paper highlights the importance of capturing non-determinism, both demonic and angelic, in the operational semantics to account for the diversity of verification algorithms used in backends. The authors provide detailed examples and rules for the operational semantics, including inhale, exhale, and sequential composition, showcasing how their approach ensures the correctness of core IVL statements for well-formed initial states. Here is a combined summary of pages 9 and 10 of the research paper. The authors formalize the operational semantics of core IVL, a verification language, and connect it to formalizations of backend verifiers, such as Viper's symbolic execution backend and verification condition generation backend. They also introduce an axiomatic semantics for core IVL, which is closer to the separation logics typically used for front-end programs, to bridge the semantic gap between the operational IVL semantics and front-end logics. The axiomatic semantics uses judgments of the form delta provable from U1D 443, U1D 436, U1D 444, where U1D 443 and U1D 444 are semantic assertions, sets of states. U1D 436 is an IVL statement, and delta is a type context. The authors prove the operational to axiomatic soundness property, which states that if a core IVL statement is well typed and valid, then there exists a set of states, U1D 435, such that delta provable from U1D 436, U1D 435, holds. The rules for the axiomatic semantics of inhale, exhale, and sequential composition are presented, which abstract over the low-level details of the dual non-determinism in the operational semantics. The authors illustrate how the axiomatic semantics hides the angelic choice behind high-level connectives such as the separating conjunction. The authors also connect the axiomatic semantics to front-end programs and logics, such as CSL, classical separation logic. They show how to construct a CSL proof for the front-end program from the axiomatic semantics, using the CSL rules and the core IVL triples obtained from the operational to axiomatic soundness property. The key benefits of the axiomatic semantics are that it contains exactly one rule per statement, with no structural rules, and that it allows for deconstructing an axiomatic semantic derivation into smaller blocks, which can then be reconstructed into a proof in the front-end logic. This enables a smooth connection between the correctness of the IVL program and the correctness of the front-end program. Formal Foundations for Translational Separation Logic Verifiers, Extended Version, 111. The paper discusses the formal foundations for translational separation logic verifiers, focusing on the decomposition of proofs for main and main_IVL into smaller parts. It highlights the exhale-inhale pattern in the core IVL code, which follows a specific sequence. Exhale the precondition, havoc the variables modified by the statement, and inhale the postcondition. This pattern is used to justify the CSL triples for statements like Q equals new cell, Q, V equals pages V, TMP equals pages V, and free, Q. The paper also presents an operational and axiomatic semantics for the core IVL language defined in Fig. 1. It first defines an IDF algebra that captures both separation logic and implicit dynamic frame state models. The IDF algebra is a tuple, sigma, circled plus, underscore, stable, stabilize, that satisfies certain axioms, including positivity and antisymmetry of the partial order induced by circled plus. The paper then formalizes the operational semantics of core IVL in section 3.2 and defines its axiomatic semantics and proves their equivalence in section 3.3. It instantiates core IVL for key features of Viper in section 3.4. The IDF algebra is used to capture arbitrary SL and IDF states, with sigma being the set of states, circled plus being a partial, commutative, and associative addition on sigma, and underscore, stable, and stabilize being endomorphisms of sigma. The paper concludes by summarizing the 3 steps involved in justifying the translational verification of the program from Fig. 2 in CSL. 1. Showing that the successful verification of its core IVL encoding in a backend implies that the core IVL program is valid. 2. Using the soundness theorem for the axiomatic IVL semantics to derive judgments in the axiomatic semantics. And 3. Using those judgments to prove the desired CSL triple. Each of these steps is well suited for its task, with the operational semantics allowing connection to the backend verifiers, while the axiomatic semantics facilitates the reconstruction of the front-end logic proof. Both linked by THM. 2. This research paper presents a formal framework for translational separation logic verifiers, focusing on the instantiation of the core IVL framework with an IDF algebra. The authors define the combination of 2 IDF states, which requires agreement on locations with non-zero permission and pointwise sum of permissions not exceeding 1. They also introduce the notion of self-framing assertions, which are stable under the stabilize function, and define various framing relations between assertions and expressions. The paper then presents the operational semantics of core IVL, with judgments of the form and bracketly t U1D 436, U1D 714, and bracketry HT right pointing arrow delta U1D 446 where delta is a type context. U1D 436 is a statement, U1D 714 is a state, and U1D 446 is a set of states. The rules for operational semantics are given in Fig. 6, which capture the behavior of inhale, exhale, and other statements in core IVL. The rules ensure that the operational semantics preserves the stability of states. The authors also discuss the axiomatic semantics of core IVL, with judgments of the form delta provable from U1D 443, U1D 436, U1D 444, where delta is a type context, U1D 443 and U1D 444 are assertions, and U1D 436 is a core IVL statement. The rules for axiomatic semantics are shown in Fig. 7, which capture the logical consequences of executing core IVL statements. Throughout the paper, the authors emphasize the importance of stability and framing in the semantics of core IVL, and provide a rigorous formalization of the framework. The work contributes to the development of formal verification techniques for concurrent programs, and provides a foundation for future research in this area. The research paper discusses the formal foundations for translational separation logic verifiers, focusing on the operational and axiomatic semantics of core IVL. It introduces the concept of self-framing, ensuring that preconditions and postconditions are self-framing, which is crucial for proving the soundness and completeness of the framework. The paper also presents a detailed proof of the soundness and completeness properties, demonstrating the equivalence between operational and axiomatic semantics. Additionally, it discusses the instantiation of core IVL for the Viper language, showcasing its practical usefulness. The backend soundness is also demonstrated through the formalization of symbolic execution and verification condition generation. The paper's technical depth and precision make it a valuable contribution to the field of formal verification. This research paper presents a formal foundation for translational separation logic verifiers, focusing on the symbolic execution backend for Viper core. The authors formalize the symbolic execution algorithm in Isabelle, whole, which is based on the description by Schwerhoff. The symbolic state tracked during verification consists of a symbolic store, path condition, and symbolic heap, represented as a list of heap chunks. Each chunk corresponds to an accree source, comprising a receive field, permission, and value. The symbolic execution is defined via the sexec function, which delegates calls to sProduce, sConsume, sCleanup, and sexp functions. These functions are formalized in Isabelle, HOL, and can be executed inside the prover to verify a concrete program. The sexec function symbolically executes a statement, inhaling or exhaling assertions, and evaluating expressions. The authors highlight the importance of angelic choice in enabling the generality of Courrevel's operational semantics. The paper also discusses state consolidation, which involves merging chunks for the same location and deducing additional information. The chunk_add function is used to model inhaling an accree source during sProduce, and the consolidate function is characterized semantically, allowing for various state consolidation algorithms. The authors prove the soundness of sexec against the operational semantics of Viper core, showing that if sexec evaluates to true, then the compiled statement is correct for the initial state. The operational semantics of core IVL is well suited for this soundness proof, as the symbolic execution traverses statements in an operational way, and it is straightforward to relate one Viper core state to one symbolic execution state. The formalization of the symbolic execution backend for Viper core demonstrates the generality of Courrevel's operational semantics, which can capture multiple common verification strategies. The use of angelic choice enables the capture of different strategies for exhaling wildcard permissions, and the soundness proof ensures the correctness of the symbolic execution algorithm. Here is a combined summary of pages 21 and 22 of the research paper. The paper presents a formal foundation for translational separation logic verifiers, focusing on the inference rules and a sound front-end translation from PAR-IMP programs with annotations to Viper core programs. The program logic judgment is written as delta provable from CSL, phi, C, psi, where phi and psi are Viper core assertions, and C is a PAR-IMP command. The most important rules of the program logic are given in Fig. 9. Which include standard rules such as s/e.sc/q.sc, c/o.sc/n.sc/s.sc, i/f.sc, and w/h.sc/i.sc/l.sc/e.sc, as well as adapted rules for the IDF setting, such as f/r.sc/a.sc/m.sc/e.sc, p/a.sc/r.sc, and l/o.sc/a.sc/d.sc. The soundness of the IDF-BASED program logic is proved in Isabelle, stating that if the triple delta provable from CSL, phi, C, psi, holds, and if sigma is a well-typed state such that phi, sigma, then executing C in the state sigma will not abort nor encounter any data race, and for all sigma, such that sigma right pointing arrow sigma, we have psi, sigma. The paper also defines a sound front-end translation from PAR-IMP programs with annotations to Viper core programs, shown in Fig. 10. The translation function takes as input an annotated PAR-IMP statement C and returns a pair of a Viper core statement and a set of Viper core statements. The translation of field and variable assignments is straightforward, while the translation of sequential composition and conditional statements is also straightforward, using the corresponding sequential composition and conditional statements of Viper core, and collecting the auxiliary methods generated by the translation of the substatements. The translation of allocation and deallocation statements corresponds to the rules a/l.sc/l.sc/o.sc/c.sc in f/r.sc/e.sc/e.sc from Fig. 9. The translation of parallel composition and while loops is more involved, but follows the same pattern, using the inhaled translation exhale pattern and the exhale Havich inhale pattern. The soundness of the front-end translation is stated in Theorem 9, which assumes that the par-imp statement C we want to verify is annotated with a precondition phi and a postcondition psi. The complete front-end translation yields the set of Viper statements: inhale phi, C.1, exhale psi, union, C.2, and is sound if the Viper statement inhale phi, C.1, exhale psi is valid, and all Viper statements in C.2 are valid. Formal Foundations for Translational Separation Logic Verifiers, Extended Version, 125. The paper discusses the soundness of front-end translations to IVLs not based on SL, 58, 3, 27, 23, 42. It highlights that the corresponding translations do not reflect rules in a front-end program logic. The soundness proofs work naturally at the level of an operational semantics for the front-end and IVL. Examples include translations from the D minor data processing language to the bemol IVL, 3, from C to the Y cert IVL, inspired by the Y3 IVL, 27, and from Viper to Boogie, 42. The paper also discusses proofs connecting an IVL with a backend. Parthasarathy et al., 42, show the soundness of the Viper backend that translates to Boogie. The work most closely related to the symbolic execution backend presented in section 4.1 is Zimmerman et al., 62, formalization of a variant of Viper's symbolic execution backend targeted at gradual verification. Due to their focus on gradual verification, they only target a simplified model of Viper that, unlike our symbolic execution, does not support fractional permission. As a consequence, they can use a simpler implementation that does not rely on continuation passing style, and they can ignore some of the complexities described in section 4.1 such as state consolidation. Also, they formalize the symbolic execution via a derivation tree, while we implement it as an Isabelle, HOL function. Vogels et al., 60, prove a formalization of verifast symbolic execution sound. Compared to our work, they do not have semantics that captures different verification algorithms, or supports IDF for fractional permissions. The paper also discusses non-SLBASEDIVL backend proofs. These backends typically have simple state models and use different algorithms compared to SLBASED backends. For example, Parthasarathy et al., 43, generate soundness proofs for Boogie's VCG, and Vogels et al., 59, prove a VCG for a similar IVL sound once and for all. Garchery, 25, and Cohen and Johnson-Frade, 12, validate certain logical transformations performed in the Y3 IVL verifier. Angelic nondeterminism has been widely used from encoding partial programs, 7, to representing interaction between code written in multiple languages, 47, 26, to encoding specifications, 22, 52. However, to the best of our knowledge, our work is the first to use angelic nondeterminism to abstract over different verification algorithms. Vogels et al., 60, and Song et al., 52, both also use angelism for exhale, but do not abstract over or formally connect with diverse backend algorithms, as we do. Instead, Vogels et al., 60, use angelism to represent a symbolic execution algorithm, while Song et al., 52, use angelism to encode the transfer of resources in a refinement calculus. Implicit dynamic frames, IDF, was originally presented with a fixed resource model, i.e., full ownership to a heap location, and where the heap is represented as a total mapping from heap locations to values, 51. Parkinson and Summers, 41, formally showed the relationship between IDF and SL by defining a logic based on total heaps and separate permission masks that captures both. They also consider fixed resource models of IDF and SL, i.e., fractional ownership to a heap location, 8. Our work generalizes the notion of a separation algebra, 9, 19, to capture arbitrary resource models for IDF and SL in the same framework. In particular, the algebra does not fix a particular state representation. This enables, for instance, a partial heap instantiation for IDF that we use to formalize Viper's state model, section 3.4. Steel Core, 55, is a framework with an extensible CSL to reason about concurrent F54 programs. The extensibility of the framework is in particular demonstrated by allowing IDF-style preconditions of the restricted form operator D443 operator D44F, compared to the more general IDF assertions supported in our work, where operator D443 is an SL assertion, and operator D44F is a heap-dependent Boolean expression framed by operator D443, and similarly for postconditions. The paper concludes by discussing other approaches to building automated SL verifiers and establishing their soundness. Steele, 24, is an SLBASED proof-oriented programming language. In F. Steele programs are automatically proved correct using a type checker that is proved sound against Steele core. The type checker uses an SMT solver to discharge proof obligations. Sammler et al. 46 propose an approach to building sound verifiers that requires writing the verifier in a domain-specific language called Lithium. Verifiers in Lithium can be automatically executed inside the Coke proof assistant and produce a foundational proof of correctness. Lithium-based verifiers are not translational, but work directly on the source language program. This research paper presents a comprehensive overview of formal foundations for translational separation logic verifiers. The authors provide an extensive list of references, showcasing the evolution of separation logic and its applications in program verification. The paper begins by citing seminal works on separation logic, including the original paper by John Reynolds, which introduced the concept of separation logic for shared mutable data structures. The authors then discuss various verification tools and techniques, such as VST Floyd, Tata, and Iris, which have been developed to reason about concurrent and parallel programs. The paper also explores the connection between separation logic and other formal verification approaches, including Hoare logic, dynamic frames, and permission-based reasoning. The authors highlight the importance of formalizing the verification process, citing works on proof-carrying code, deductive verification, and certified verification. Furthermore, the paper discusses the role of intermediate verification languages in facilitating the verification process, referencing works on Viper, Steele, and Crousat. The authors also touch on the topic of automated verification, citing research on verification algorithms, symbolic execution, and proof assistants like Isabelle, HOL, and Coke. The paper concludes by emphasizing the need for trustworthy automated program verifiers, highlighting the importance of formally validating translations into intermediate verification languages. The author's comprehensive survey of the field provides a valuable resource for researchers and practitioners working on formal verification and separation logic. Throughout the paper, the authors demonstrate a deep understanding of the subject matter, providing precise explanations of technical concepts, such as fractional resources, magic wands, and implicit dynamic frames. The paper's technical tone and attention to detail make it an authoritative reference for experts in the field. The research paper discusses the formal foundations for translational separation logic verifiers. It presents a detailed overview of the main functions involved in symbolic execution, including sexec, sproduce, sconsume, and sexpfunc. These functions are used to symbolically execute statements in a symbolic state, producing and consuming assertions, and executing functions. The paper also explains the definitions of these functions, highlighting their purpose and significance in the context of symbolic execution. The authors provide a comprehensive description of how these functions interact and contribute to the overall process of symbolic execution. The paper concludes by emphasizing the importance of these functions in ensuring the correctness of programs through formal verification. The research paper discusses the formal foundations for translational separation logic verifiers, focusing on the symbolic evaluation of expressions in a symbolic state. It defines a function that evaluates the expression in the given state, considering the treatment of lazy binary operators. The paper also introduces the concept of a function that defines the behavior of the verifier, including the handling of equality and inequality checks. The summary highlights the novel ideas and significant findings presented in the paper, including the definition of a function that evaluates expressions symbolically and the introduction of a new concept for handling lazy binary operators. It also emphasizes the importance of the paper's contributions in the field of separation logic and its applications.